In this video, we're going to cover section 7.4, which is titled Area and Arc Length in Polar Coordinates. And in it, we're going to be looking at some applications of the polar coordinate system that we discussed in the last section. And I think the title is pretty descriptive. There's basically two applications. One is we're going to find the area of regions inside polar curves, and then the other one is we're going to find the arc length of a polar curve. These are both things that we've done before with the rectangular coordinate system. We're now going to take a look at how to do it with the polar coordinate system. And so we have a figure here shown, figure 7.39, and it kind of it shows a polar curve here in blue, and you can see that it's breaking up this polar area, if you will, into small subregions, kind of like we thought about when we had, you know, a Cartesian equation, y equals f of x. We would find the area under the curve by breaking it into small rectangles and find the area of each one of those rectangles, and then adding it together with an integral. It's the same concept here. We're not going to get into the weeds of that, but what I do want to discuss, though, is, well, from the formula, so Theorem 7.36, or Theorem 7.6, it says the area of a region bounded by a polar curve. And it says, suppose f is a continuous and non-negative on the interval, theta goes from alpha to beta. Now, this is the part I really want to discuss, because say this is our area right here. So we have all this area. The important thing to remember is that as we accumulate that area, we always start with the smallest angle and we move to the biggest angle. So if theta is equal to alpha right here, and theta is equal to beta right here, we're going to accumulate area in the counterclockwise direction. We're going to add it up, and it's just going to kind of fan out like this. It's going to fan out. It's going to pick up all this area as we move in the counterclockwise direction. So, and I think the easiest way to see how this works is with a graph. So we have Theorem 7.6. We have example 1. And it says, find the area of a polar region, determine the area of the inner loop of r equals 2 plus 4 cosine theta. So we have a specific graph. Let's go ahead and take a look at what that looks like in Desmos. R equals 2 plus 4 cosine theta. All right, so we have r equals 2 times 2 plus 4 times cosine theta. And this is a lemicon, which we know has these sort of inner loops. So let's go ahead and snip a copy of this. Okay, so example 1, again, it says determine the area of the inner loop. So the part that we're looking for is we're looking for this part right here. And that part in the middle there, so it's a loop, and if you were to actually like watch this draw out as theta increases, it actually starts with, kind of highlight at the origin here. It starts at the origin and it follows around and it comes back to the origin. Well, what's the value of r at the origin there? What is r equal to? Well, hopefully you're saying at the origin it hasn't gone anywhere, so r equals 0. And that basically is how we determine our bounds for theta, because we need to know the range of values that theta is going to move through as r draws out this part of the curve. So in order to do that, again, because r is 0 when the loop starts and stops, r is 0 when the loop starts and stops, we're going to take our equation and we're going to set r equals 0 for that equation. So let's write that out. The inner loop starts and stops where r equals 0. So we take our equation then. We have r equals 2 plus 4 cosine theta, and we want to let r equal 0. So we have 0 equals 2 plus 4 cosine theta, and this is going to tell us, if we solve for theta, the angles where that's going to happen at. So this is where trig comes in. If you haven't noticed yet, there's quite a bit of trig in this chapter. So we want to subtract 2 to the other side. We have negative 2 equals 4 cosine of theta. And then we can go ahead and divide both sides by 4. So we have negative 2 over 4 is equal to cosine theta, or negative 1/2 equals cosine theta. And then you use our inverse cosine, right? So theta is equal to the inverse cosine of negative 1/2. Well, cosine is negative in the, what is that, the second and third quadrants, and the values of theta that we're going to have where you get negative 1/2 in those second and third quadrants is going to be 2 pi over 3 and 4 pi over 3. So you got to be able, this is all pre-calculus stuff, you got to be able to solve for theta. And then once you have that, then it's just a matter of setting up your integral. So if we go back real quick though to that picture, so basically what that means is, I'm going to erase that red stuff and then we'll go back here. So look, 2 pi over 3, that's right here. 2 pi over 3 is where that loop starts. Then it comes around and it finishes at 4 pi over 3. Well, here's 4 pi over 3 right there. It finishes there. So it starts at 2 pi over 3 and it finishes at 4 pi over 3. And it's going to fill up all that area. So we go to our graph and we have this integral. We know it's going to go from 2 pi over 3 to 4 pi over 3. And looking back up at the Theorem 7.6, we know we have that area is 1/2 of that integral times the function squared. So our function is 2 plus 4 cosine theta squared d theta. And that's how we set up this problem. Now if you actually square all that out, you get 1/2 integral from 2 pi over 3, 4 pi over 3, and that comes out to what, 4 plus 16 cosine theta plus 16 cosine squared theta. And I'm going to leave the actual, I'm going to post the solution for how you finish out this problem. You have to use, in order to get this part, you have to use stuff that we did in, what section was that? That was the trig integrals. I believe that was section 2.2. 3.2, I mean. So section 3.2. So make sure you go back and review section 3.2 if you don't know how to deal with cosine squared. Again, I'm going to post the full solution to this in your notes. Now, before we move on to the next example, one thing I did want to discuss, I haven't showed you yet how to do polar graphing on your graphing calculator. We've only done it on Desmos, but it is important to be able to do this on a graphing calculator. So I'm going to pull up my graphing calculator here, and let's turn it on and go to the mode. So the last time we were here, we had it in parametric mode, but we now want to have it in polar mode. So you get mode, and you go to polar, press enter. And then when you go to y equals, you'll notice now it's in r equals form. So I'm going to go ahead and put in my equation. I have 2 plus 4 times the cosine. And remember our x button? So when we were in parametric form, it used t. And then when we were in theta form, it used, or now that we're in polar form, it's going to use theta. So if I go ahead and press that button, I'm going to get a theta, close parentheses. And let's go ahead and graph and see what this looks like. So yeah, it's just like the one we saw in Desmos. Now here's where this is kind of nice. So if we go to the window, we can change. I like to use the graphing calculator to kind of check to make sure my bounds are okay. So remember, our integral had the bounds 2 pi over 3 to 4 pi over 3. Let's go to the window and let's change those theta bounds. So let's make our theta min. Let's make it our lower bound. Let's make it 2 pi over 3. Press enter. And then let's do our upper bound, make that our theta max. So let's go 4 pi over 3. Press enter. And if we did our bounds correctly, we would expect now that our graph, when we hit graph, will only show the inner loop. So let's go ahead and confirm that that works. So if we hit graph, you can see that it draws out the inner loop. Of course, we could zoom in here. We could go to zoom in so we can see that better. But yeah, we got our inner loop there. Our bounds were correct. So let's go ahead and take a look now at example 2. Example 2 also says to find the area of a loop, but this is a different polar curve. You should recognize that because of this 3 theta here, this is a rose. This is a rose with 3 loops. But let's go ahead and take a look at what this graph looks like. So if we go to our graphing calculator, why don't we do this one with our graphing calculator? So we can go back to y equals, clear this out, and we can go 4 times the cosine of 3 theta. And I'm going to go ahead and hit graph. And you can see, first of all, that we have some problems with our bounds. Remember, we changed them in the last one to different bounds. So let's go back to, let's just go 0 to 2 pi. Let's see what that does. 0 to 2 pi. And hit graph. Now we get the whole thing, but we still don't see it all. So I'm going to hit zoom and go just option 6 for a standard window. And so there we see our 3 looped rows. And we want the area of just one of those loops. So, you know, I still don't love the fact that this is so small. I'm going to change my, we don't need it necessarily to go from -10 to 10. How about if we go like -6 to 6, and we'll go -6 to 6 in the x and the y direction. And let's do graph now. Okay, now we got a little bit of a bigger picture. And I'm going to go ahead and take a screen capture of that graph here. And so that the area that we're looking for again, right, the area we're looking for is one loop. And again, it's the same idea, because right there at the origin, what's r equal to? Well, again, r equals 0, right? So we're going to do the same concept here. We're going to come back with our curve, and we're going to set r equal to 0. We're going to let r equals 0. And when we do that, we get 0 equals 4 times the cosine of 3 theta. All right, again, how are your trig skills? Let me document our steps here. Our first thing is we want to get the cosine by itself, so we're going to divide by 4. And so when we divide by 4, we're going to get 0 equals cosine of 3 theta. And we got to use inverse cosine again. So when we use inverse cosine, right, we're going to get that 3 theta is essentially equal to the inverse cosine of the other side, so the inverse cosine of 0. Well, where is cosine equal to 0? It's at 2 places, right? Cosine is equal to 0 at pi over 2 and 3 pi over 2, right? That's on the y-axis. Cosine is the x value. X's are 0 on the y-axis. So at pi over 2 and 3 pi over 2, that's 3 theta. It's not theta, it's 3 theta. So if we want to actually figure out what theta is, now we need to divide both sides by 3, right? Divide both sides by 3. That's going to tell us theta. Pi over 2 divided by 3 is pi over 6. And 3 pi over 2 divided by 3 is pi over 2. All right? So if we go back to our graph, look at our graph here. Well, pi over 6, just looking at the graph here, more than likely pi over 6 is probably going to be right there. And then pi over 2, of course, is right here. So that's going to be where probably this next loop starts. Right there, it starts at pi over 2. So that's not really going to be helpful from us. We don't want to go from pi over 6 to pi over 2 because that's going to not give us the area we want. In fact, it looks like we might want to go start from here, and with symmetry, what's that angle going to be, right? So if we remember, we sweep around in the counterclockwise area to pick up area. So what's that angle going to be? Well, by symmetry, we know that would be negative pi over 6, right? So if we sweep counterclockwise from negative pi over 6 to pi over 6, we're going to get this area inside this loop, I think. But how can we verify it again? Well, let's go to the graphing calculator. Let's actually change our limits and verify that that works. So if we open up our graphing calculator, and we go back to window to change the limits, let's make theta min negative pi over 6, and let's make theta max pi over 6. And let's verify that that actually gives us that one loop. And there it is. So we have one loop of the graph, which makes the rest of it pretty easy. We know that the area is equal to 1/2 of, and our theta, in this case, is going to go from negative pi over 6 to pi over 6. That's the hardest part. And then we have our function, 4 cosine of 3 theta squared d theta. And of course, when we square it, we have to square the 4 and the cosine, so that's going to be 16. So we have the integral of 16 times cosine squared 3 theta. And we can simplify the 1/2 into the 16. It's going to make this an 8. Again, in order to evaluate this, we're going to use the methods from section 3.2. So I'm going to put the rest of the solution here in your canvas. I'm going to post the solution. We don't have time in this video to go over how to do that. We've covered that already in this class. Make sure you look at the full solution and copy that into your notes. I also suggest that for both examples 1 and 2, you do include in your notes the sketch of the graph so you can reference back to that. When you're doing the homework and the lab assignments, you should also sketch the graph on your homework. I'm going to expect that on the test for you to show a sketch. One thing I haven't showed you yet is that at the end of section 7.3, there was some polar scratch paper that you can go ahead and use to do sketches of graphs as well. So anyway, that is what I have for this first video. In the next video, we're going to take a look at finding the area between two polar curves. That's a little bit different than what we've done so far in the first 2 examples. Thank you. See you in the next video.